My name is Ritik Dattuk, and I'm a PhD student at the ASUP's lab. I'm going to talk about my research project in this video. The project title is Coordinated Control and Cybersecure Communication in a Distributed Host Nation Microgrid System, which is funded by the Office of Naval Research. The project lead is Dr. An Malik, and I'm working under his supervision on this project. In foreign countries, the Department of Defense needs a reliable source of power. Harnessing the power completely by their own increases the cost multifold, as well as poses different threats, resulting in a vulnerable operation in the foreign bases. Therefore, a reliable, resilient, and a cost-effective microgrid installation that has the ability to interface with the host nation power grids and alternative energy assets is needed, which will have a cyber-secure communication system. In this project, our team will try to develop the performance indices of host nation-based coordinated microgrid system, incorporating a Kalman filter-based feedback controller to provide a reliable and economical solution to the existing microgrid problems. So this work is a collaboration between ASU Peace Lab and ASU Libs Lab. The Peace Lab will integrate the host nation power grid with the microgrid and evaluate the power quality of the whole system. It will also work on the enforcement of the cybersecurity of the microgrid. The Libs Lab will work on the adaptability and control of the microgrid. The duration of this project is 1.5 years and it is expected to end in September 2024. The objective of this project is divided into 4 tasks. The first one is the evaluation and development of the power quality performance indices of host nation microgrids. We will study and develop these performance indices of the host nation based microgrids: power factor, displacement power factor, total harmonic distortion, and electromagnetic compliances. Then we'll determine the cost benefits and efficiency of the AMS generator using this equation presented in the slides. Our microgrid model, which is designed in MATLAB Simulink, the host nation grid is connected to the microgrid through the three-phase circuit breakers. So the AMS generator is also connected to the microgrid through the three-phase circuit breaker. So when the grid is operating, the microgrid is operating at the island mode. So then the three-phase circuit breakers will close and let the AMS generator connect to the system. The PV array is connected to the DC microgrid through the MPPT, and the battery is also connected to the DC microgrid through a DC-DC power converter, which is typically a buck boost converter to regulate the battery terminal voltage. There is a DC load and a AC load. The DC load is connected to the DC side of the microgrid, but the AC load is connected to the inverter or the AC side of the microgrid. In this slide, there are multiple cases where the microgrid is connected to the grid system. So we can see 4 cases where different sorts of power flows are happening. In case 1 and case 4, the PV array is participating in the power flow, while in the other 2 cases, the PV array is not generating any power. So mainly the grid is supplying power to the load and also to the battery when needed. Here, 4 different cases are presented where the microgrid is now operating at island mode. So the host nation grid is not connected here. So the PV array, battery, and the AMS generator, these are 3 sources of power in the microgrid. In these 4 cases, the AMS generator is not generating any power, so it is basically disconnected from the microgrid. The PV array and the battery is supplying power to the load, to the AC and DC loads, and when the battery is depleted, the PV array is mostly supplying the power here, and sometimes it is also charging the batteries as well. In the last 3 cases, the AMS generator is also participating in the power flow. So mainly the AMS generator is supplying power to the loads, and it is also charging the batteries if the battery charge is below a certain point. At the same time, when the PV is generating power, so it is sharing the load requirement with the AMS generator, and sometimes the battery is also supplying power to the loads. The inputs of the microgrid model is they are shown here. The solar cell we have used is parallel series string connection, while their maximum output power will be 1 kilowatt. Here the MPPT is used, and the irradiation is given as an input, which is shown here. The battery is 160 volt 300 ampere hour lithium ion battery pack, and it is connected to the DC bus through a buck boost converter. The grid is a conventional 120 volt 60 Hz infinite bus system, which is connected to the microgrid through a three-phase circuit breaker. The amps generator we used in this model is the rating of that is 250 volts 3000 volt amperes 60 Hz synchronous generator, which only operates in the island mode operation, as the grid is considered an infinite bus, and it is also connected to the microgrid system through a three-phase circuit breaker. The loads we used in this case, they are both 500 resistive load. The AC load is 500 watt resistive load, while the DC load is 250 watts resistive load. So this is a scaled down model of the whole microgrid system. Once we establish our cases here, we'll try to scale it up and simulate for the whole original model. Here, the result of a single case, case 4, is shown, where in the case 4, the grid is supplying the power to the loads and the battery pack, while the PV power is being flowed into the grid. And with the grid connected to the microgrid, it is expected that the input three-phase voltage of the microgrid will have really low THD, and the voltage waveforms are better, which is shown in the right picture, where we can see the voltage waveforms are really good, and we can anticipate from this figure that the THD of this of the microgrid input will be also good. So as mentioned earlier, the THD here is only 0.04%, which is really low. And as the battery is also charging from the grid and also the PV, the state of charge SOC of the battery is also increasing. So it has increased to around 87% from 70%. So in these 2 hours, while the charging is happening at 25 amps of current. Second task is to develop the cyber resiliency of the host nation microgrid connected power converters, so that in any situation the security of the whole microgrid won't be compromised. The model will be developed using MATLAB Simulink, and different sorts of attacks or faults will be programmed through FPGA, and it will be sent to the microgrid. So in order to prevent those, the microgrid will also have a control algorithm based on Kalman filter and convolutional code, and it will detect the attacks and then will prevent those likewise. So the third task of this project is the enhancement of adaptability of controls for improved grid power exchange, so that even if something happens to the grid or the power quality of the grid, it falls, the microgrid control will take over the situation and it will take necessary steps. As mentioned earlier, there will be adaptive power dispatch and energy management strategies in real-time operations. There will be many open source optimizer solvers to locate the loads or locate the power flow. And during the contingency events, in every 15 minutes interval, there will be some control decision which will be conducted by the economic dispatch, while the distributed energy resource segments are chosen to minimize the grid connected operation cost. The final task will be the evaluation of intelligent controls of hybrid microgrid assets for host nation power grid, where different sorts of test beds will be used to evaluate the efficiency of the whole microgrid. ASU microgrid testbed will be used to demonstrate different control algorithms on a 30 kilowatt hybrid microgrid system, which will have Blue Planet battery storage, AMPS digital generator, NHR and Chroma load management system, and Chroma grid emulator. With this and Opal RT real-time simulator, we'll try to model a host nation power system, and the Chroma grid emulator will be programmed to simulate an unreliable host nation power grid. With these things and with the help of SCADA capability, we'll try to simulate the faults and attacks, and we'll try to prevent those using the Kalman filter based technologies. So thank you everyone for staying here, and if you have any questions or any doubts regarding this project, you can contact me via this email. So I'd be happy to hear from you. Thank you.